So we have two topics to do, so we'll do the first one here. Okay, so we're going to have a look at photons. Can you see okay? Yeah? Okay. So we're going to talk about photons, what they are, the equations that we have for them. We'll be using electron volts again and talking about some work Einstein did as well. Okay, so first I just want to give you some useful English vocabulary. This is maybe a word you don't know. Or maybe Abraham, I don't know. Would you know this word, quantum? Quantum mechanics, correct? Yep. And quantum of solace, the James Bond movie. No, we don't know this one? Yeah. So would you know what quantum means? No, okay. So quantum, or quanta, is the minimum amount of any physical entity involved in an interaction. So in other words, a quantum is like the smallest piece. So atoms, they're like quanta of matter. Because what's the smallest piece of matter you could have is an atom. So you could almost say the quanta of matter is atoms, as an example. So quanta really means the smallest piece. Okay. What do you think a quanta of a class is? Well, I'd say probably the student is the smallest piece. Can you have half a student? No. Can you have half an atom? No. Okay. So quantum, please make note of this, it's like the smallest piece. Now this isn't a definition for the exam, this is just a definition for your English. Yeah. I know what you're going to ask me, and I'm sorry I don't have it yet. I'm sorry. That's what you're going to ask me, isn't it? Yes. Not after the exam? You want it before the exam? I try my best. No, that's not what he wants. He wants the definitions for the exam. Okay, can I go to the next slide? You got it? Yeah, okay. So far we have no need for quanta. We didn't need it. For example, we don't have quanta of distance. I mean, distance, there is no minimum. Distance can be any number, you know? You could have like 10 to the minus 10, 10 to the minus 11, 10 to the minus 12. You can have whatever distance you want. There's no minimum distance. You can have 10 to the minus 100 if you want. Etc., etc. Okay. So a definition now, a photon is a single quantum of light. And it's called a light photon. So in other words, a photon is the smallest amount of light that you can have. It's like the minimum amount of light. Is a photon. Yeah? Yes? Yeah? Okay. Sorry, can I go on? So we should think of light as a group of photons. So we should think of light as lots of little photons of light. Like in biology, we have a person and we think of them as little cells. Or in chemistry, you have matter and we think of it as atoms. Make the matter. So for light, we think of all the photons that make the light. Okay? So just to be very clear, you can have some distance, a smaller distance, an even smaller distance, an even smaller distance, an even smaller distance, an even smaller distance, etc. No smallest. Agreed? for light, you could have some light, smaller, less light, less, and there's the smallest, which we call a photon, and then after that, no light.
So does photon have a mass?
No, zero mass. It is massless, no mass. So are we all clear what I'm saying here with photon? Yeah. So a photon is like an atom. This is the idea that we have. An atom of light, the smallest part. So it's the smallest, and there's nothing smaller. You don't need to write this down, but I'm saying here a photon is a particle of light. No, I think it actually is good if you write this down. So we talk about light as being a wave, but we can think about these photons as being like particles, small little pieces of light. They act like what? Electrons? What do you mean? Yeah, we'll be talking about double slit. One step at a time. One step at a time. No, one step at a time. One step at a time. Okay, can I go on? You'll see, don't worry. Don't worry. Okay, I can go on? Okay. Einstein discovered that the energy of a light photon, or other electromagnetic radiation, it depends only on the frequency of the light. That is, the higher the frequency, the higher the light. So Einstein discovered that the only thing you need to know is the frequency. If you know the frequency of the light photon, then you can know how much energy it has. The formula is very simple. The energy is equal to this Planck constant multiplied frequency, and the value of this constant in the formula is this number here. This is a number you will use and see in chemistry, and in fact you will see this formula in chemistry too, except Lorraine will write it a little differently. In chemistry, Lorraine will write the formula like this: E equals H nu. But in chemistry, this just is the letter they use for frequency. So it's the same formula in chemistry. Have you done this in chemistry? No, you'll probably do it tomorrow then. So you need this formula and this constant here. So think about it like this. Which has a bigger frequency? Red, orange, yellow, green, blue, indigo, violet. Of all those colours, which one has the biggest frequency? Violet. So that means violet light has more colour, more energy than red light. Yeah? Okay. Can I go on? Yeah? So let's have a look at a simple example. A photon of red light has a wavelength of 400 nanometers. What is the frequency of this light, and how much energy does this photon have? Okay, let's have a look. So what's the wavelength? I said it's 400 nanometers. And how can I calculate the frequency? What formula? Yeah, that one there. C equals F lambda. So F equals C over lambda. So F equals 400 multiplied 10 to the minus 9, whoops, wrong way. 400 multiplied 10 to the minus 9, 3 multiplied 10 to the 8. Can you calculate this for me, please? And it'll be in hertz. What is it?
Very deep.
Yeah.
1.5 times
to the what? This is it? Yeah. So that's the first part. Now the second part is what is the energy of this photon. So we think about it like this. Here is my photon of light, and it's moving along at speed c, and its frequency is here. How much energy does this light photon have? Well, the formula is very simple. Its energy is its frequency multiplied this Planck constant. What did I say the Planck constant was? 6.626 times, times 7.5 times 10 to the 14. So, what do we get here? How many joules of energy? 4.9 times 10 to the minus 19 joules. Yeah, well, it's only one photon. This is the reason why. That's the question we'll do in a moment. Don't worry. See, I'm thinking about everything. Don't worry. Okay, can I scroll down? Yeah. Okay. Oh, and now for the next part, the last part is how much does this have in electron volts? Do you remember how to change this into electron volts? Yeah, which?
I think divide.
You are correct. We have to divide it by the E constant, which is, I don't remember right now. Yeah, the charge of the electron. It's on your calculator.
One.
1.6. 10 minus 19? Don't think so. Oh, sorry, you're giving me the E, not the final answer. Thank you. What is it, Louise? 1.6 times 10 to the... Yeah. So the reason we use electron volts instead of joules is it's a small unit. It makes it more suitable. And so what is the value here? It's about 3 or something? Can you calculate? Really, these cancel. So it's only this part here. 3.1 electron volts.
So index is a way to...
No, only if they say so. Like I did here. Okay? Now, let's look at another question, which is what you were saying. Oh.
It's the question, they write the number as the unity, they will change it after.
No, if they don't say how they want the answer, you can change it or not change it. Now this is what you were asking me, Who. Your mobile phone has a frequency of about 900 megahertz and a power of 4 watts. So how many photons are coming out? Because if you think about it, your phone is like this. Here's your phone. And there is a wave coming out, isn't there? Like a radio wave. But this wave is made up of little photons. Lots of little photons. So my question is, how many photons? So I tell you that the frequency, what did I say, was 800 or 900? Oops. 900. Back here. The frequency is 900. In fact, I don't know what the power is, megahertz. I said it's 4 watts. I'll tell you what mine is. It doesn't matter. Something like 4 watts. And my question is, how many photons? Okay, so the first thing we do is we work out the energy of one photon, of just one photon, like this one. This would be HF, which would be 6.26, was it? Times 10 to the minus 34. Oh, 62. Yes. And then multiply by 900, multiply 10 to the 6 for mega. Can you tell me what this is, please? Now, it'll be really small because there's only one photon.
Almost.
5.96 times 10 to the minus 25 joules. So that's how much energy one photon has. Now think about this. If the power is 4 watts, what's the formula for power? It's work over time. Now I think I should say in the question per second. No, I don't, but I do mean per second. So if I have per second, what's the time here? It's just 1. So if the power equals 4 watts, then how much energy is that per second? What's the work, the energy? It's 4 also, because the T is just 1. So you have work equals power multiplied time. The time is 1, and the power is 4, so the answer is 4 joules. So in total, how much energy is coming out of the phone? 4 joules per second. And how much energy does one photon have? It has this much energy. So if I want to know how many photons, divide, yeah. So the number of photons would equal 4 divided by 5.96 times 10 to the minus 25, which will be a huge number. So you can see per second, this is how many photons are coming out of my phone per second. This is what you wanted to know. Yes. So it's a big number. Yeah? Okay. So we can continue then? Let's see. Okay. You would know from chemistry also that electrons are trapped. They're in like if they're in an orbit, they need energy to be freed, and this is called ionization. And just like in physics, a similar idea, electrons can be trapped on a metal surface, and they require energy to be freed. So if I have some metal, there's electrons on it, and if I want to free the electrons, I need to give it energy. So what way could I give it energy? I could heat it, for example. That's one way of doing it. Therefore, they have negative potential energy. The energy required to free the electron is called the work function. So I'll just explain that now a bit more clearly now in a moment. What I'm saying here is, if I have some metal, we picture little electrons on the metal, and they're trapped. And if I want to free the electron, I need to give it some energy. So we suggested we could put in some heat. So if I put in some heat energy, I can give the electron its energy it needs, and it can be freed. And we say that the electron has negative potential energy here. And when it's freed, its potential energy becomes 0 then. How much energy do we need to give it? Well, that is called the work function, which is my definition here. The work function is the minimum energy needed to remove an electron. So, in other words, work function is like ionization energy. Got that? Got that, Jeff? Now there is another way to give the metal energy. We could heat it, or we can put some light on it. So when photons strike some clean metal, some of the electrons will be freed. So heat, of course, will do as well. But in fact, light also works. So if the light comes in and hits the metal, maybe some electrons can be freed. This basically is called the photoelectric effect. So maybe my definition is a little bit too long, but if you want, you can just say photoelectric effect is freeing electrons by using light. So you don't need to write all of that. You can just write the photoelectric effect is the freeing of electrons by using light photons. Here, I'll write it down. Don't you worry, I'll write it down. The photoelectric effect is... Oh wait, do you have it?
I have it.
Read it back to me.
Photoelectric effect.
Yes.
It's freeing of electrons by using light photon.
Correct. Do you have it, Louise? Yeah? Did you have it as well, Abraham? Okay. Now here's a very, very simple experiment to show that. You see, here is my metal, and you can see there's the electrons on it. Yes? And what happens is, some light comes in, the electrons get freed, they will jump over to this metal plate, and then they'll go around and make a circuit. So they will light the light. And here's your ammeter here. This is in a vacuum. Why do you think I need to put this in a vacuum?
Because it is not vacuum. The electron
Yep.
might heat some.
Yeah. There's no vacuum, the electron might hit the air molecules. You need this in a vacuum. So the light comes in, it frees the electron jumps here and then goes around and makes a circuit. So you could do some work. You can, oh well actually this one here is, I don't know why the battery is here, this isn't quite what I want. I don't like the battery here. Pretend the battery's not here. The electrons come around and they can make a circuit. In fact, if you think about it, this is a solar panel. Solar panel, because the sunlight comes in, it frees the electrons travel around and they make a circuit. You can do some work, you can measure the current. And you all have one, right here. Here it is here. So the light comes in, it frees the electrons, and then the electrons move around and make a circuit. Yeah? So, it's very simple device. You know, you just need 2 sheets of metal, nice and clean. You see it's all clean. And then it needs to be in a vacuum. So, I think this is like a vacuum, but it's a very small vacuum. So, I think if you break this, you know, if it cracks, I don't think it will work. Because then the air gets inside of it. I think so. I'm not 100% sure if this is the same one as that, but it's similar to it. Yeah. Okay, so I'm going to look at 4 possibilities here. So you could have low frequency and low intensity. When I say low intensity, I mean dim light. What does dim mean? Weak light, not so bright. So tell me what you think would happen. If the frequency is low and the intensity is low, do I have much or little electrons? Little electrons. And will they be going fast or slow? So, good, okay. So this means some freed electrons of low kinetic energy. Okay, so I think you should write this table down. There's going to be 4 possibilities. You know, we are going to do all four, yes. Okay, the next one. High frequency and low intensity. What do we predict would happen? So if it's high frequency and low intensity. So do you think there'll be many or a few electrons? A few electrons and fast or slow energy? Do you think fast?
Maybe T.
Okay, let's think for a minute first.
High frequency, higher energy.
Correct. The photons have higher energy.
So it moves fast.
So, which moves fast?
The photons.
Well, the photons all have the same speed. See? Yeah, think carefully.
But the electron has higher kinetic energy.
Let me give you the answer. Let's see what we get. So, if the frequency is high and the intensity is low, then you have some free electrons of high energy.
Yeah.
So some electrons are freed and they have high energy. Okay? Now, next, since you're so great. If you have low frequency and bright light,
The kinetic energy must be low.
so kinetic energy low, and
High frequency, more electrons, or some electrons.
correct, many freed electrons of low energy. Okay. Now, the last one, high frequency and high intensity. What do we have? Here, well, no surprises. Many freed electrons of high energy. Yeah? Okay. This is all called photoelectric effect. In other words, freeing electrons by using photons. Can I continue? Yeah. Okay. In fact, if you think about the formula, it's like this. At the start you have a photon. What's the energy of the photon? Hf. Remember I gave that formula. And then what's the energy of the electron? It's minus the work function because, why minus? What's the word I use? It's because it's trapped. So that's why it's minus. So what happens? The photon comes in, hits the electron, and then what happens now? The electron is moving away. So what type of energy does it have at the end? It's moving. It's kinetic energy. So this is the energy before it hits the metal plate, and then this is the energy after. And we know from physics that this should be the same. Normally this formula is written like this though, where we just take this over here to make it a plus. And this formula here is for the photoelectric effect. So the energy of the light equals the work function plus the kinetic energy of the freed electron. So, if I make the photon have more energy, this does not change. This is just a value for the material. So this does not change. So if I make this F bigger, then what must happen here? Bigger. So how does the electron have more kinetic energy? What will happen to it? It's moving fast. Okay? So high frequency, fast electron. Lower frequency, slower electron. Make sense? In fact, this is what Einstein won the Nobel Prize for, is this formula. So Einstein is the person who studies this photoelectric effect, and he had this formula, and this is what he won the Nobel Prize for in 1920, whatever. Yes, instead of that one. True. Most people think it's that one. In fact, it's not. It's this one. Okay. Alright. So let's have a look at an example. So here I have some copper, and I have a photon that comes into the copper, and it hits the copper, and then an electron is free. What is the work function in joules? Is the first question. So convert to joules. And then next, what is the speed of the electron after it's freed? Okay, so let's have a look at those. Let's do that together. We need our calculator. So can you just write the numbers down? This is the work function and this is the wavelength. Okay, can I go to, you really just need the numbers here, is what's most important. Okay, so let's draw this. Here's my metal. Whoa. What did I say the work function is? Electron volts. And then here comes my photon. And what is the wavelength here? 550 nanometers. And then this hits electron, and then the electron is freed. Off it goes with a velocity of v. So my first question is to convert this into joules. So how do I convert this into joules? Yeah, so it's multiplied by 1.6 times 10 to the minus 27? Thank you. Are you sure?
Yes.
Well, maybe you should.
Yes, it's nice. I have the answer.
Okay, so what's the answer then here?
7.53 times 10 to the minus 9.
Okay. Joules. Now, if I want to calculate the speed of this electron, I use Einstein's photoelectric formula, which says hf equals work function plus Ke. Now, do we know the frequency?
We know.
We almost know it, because we know the wavelength. So I can use C equals F lambda, F equals C over lambda, so F equals 3 times 10 to the 8 over 550 times 10 to the minus 9. So, what's that? What is it, sorry?
5.45
Yeah.
times 10 to the 14.
And then here is H. What did I say H was? 6.26, wasn't it? 10 to the minus... I say mistake. 626. So 63 times 10 to the minus... Okay. I would like to know what the kinetic energy is. So on your calculator you'll need to do this. 6.63, 10 to the minus 34, 5.45, 10 to the 14, minus 7.53, 10 to the minus 19. So what's my kinetic energy?
I have 3.91.
Minus 9 joules. Yeah? Yeah, we shouldn't trust him. Definitely not.
Sometimes you should.
Sometimes we should, and sometimes we shouldn't. Leave him alone, let him do it. Louise, did you get this answer?
Yes.
He's right? Good, okay. Now, I'm not finished because I think I asked for the speed. Yeah. So what's the formula for kinetic energy?
Half
A half mv squared. Now the mass of the electron is on your calculator. So you have V equals square root 2 times 3.91 times 10 to the minus 19. Can you tell me what's the mass of an electron on your calculator?
9.1.
Oh yeah, 9.91, isn't it?
9.1 10 to the minus 13.
Is it 9.1 or 1.9?
1.0.
So 1.1 then. Okay, so what do we get here?
very fast.
Oh yeah, should be pretty fast.
9.269. Very fast.
Yeah, 10.
6.
That's okay, yeah. Yeah, yeah.
9.27.
9.27
9.37.
times 10 to the 6 meters per second. Yeah, go ahead, Joe, it's okay.
Sorry. How is that? No, sorry. 5.
Are you sure now? All right. Yeah? Okay. I'll go back now. So, the work function, this means the electron has this much energy, minus. And in order to free the electron, we need to give it that much energy. Hang on, I'm stuck. If a light photon has exactly this amount of energy, then the electron will just about be freed. That is, so I'll just maybe go on the side here. If we think about the formula, it's HF equals work function plus kinetic energy. So look, if this frequency is very big, what happens to the electron? Is it fast or slow? We said it earlier. If the F is very big, then what happens here? It's fast. Now suppose I make F smaller and smaller. What happens here? It gets smaller and smaller. And I want the electron to be free, but not moving. So how much kinetic energy should it have? 0. So this formula here is like the minimum frequency to free the electron. So I'm saying the energy equals HF of the photon. If I make this equal to the work function, in other words, no kinetic energy, then it's just enough energy to free it. This frequency, which is the work function over H, that's called the threshold frequency. It's the frequency that will just about free the electron. So the definition here is what I care about. The threshold frequency is equal to the work function divided by h. So just to be very clear, this frequency is the minimum frequency to free the electron. If the frequency is smaller than this, the electron won't be free. If the frequency equals this, the electron will be free. And if the frequency is more than this, then the electron will be freed and have kinetic energy. So let's have a look at an example. The work function for gold is 5.1 electron volts. What is the threshold frequency? So let's have a look at that. So here's my gold. What did I say the work function was? 5.1? So in joules, that would be what? Yes. So here are my electrons. And what I would like to know is, what is the minimum frequency I need so that I will just about free an electron, but it doesn't really move. It's, just freed off the surface, but it's not moving.
Do they have the
You definitely do. 6.6.
1.2.
You're giving me the next answer, is it? Yeah, let me just write it down here. So the threshold frequency is work function over h, which is 8.17 times 10 to the minus 19 over 6.62 minus 34, that's a 19, equals, what did you say, Ibrahim? 10 to the 15 hertz. So if the frequency is equal to this, the electron will be freed. Just about. My next question is, how much energy would the electron have if the frequency is twice this? So if the frequency is twice this, how much energy will it have? Well, the frequency would be this. True. Twice this number. And I can calculate the kinetic energy by using Einstein's formula. So the kinetic energy would equal this. So that would be I would have to do 6.62 10 to the minus 34 2.4 10 to the 15 minus 8.17 10 to the minus 19. So what do I get? That's it. 10 to the minus 19 joules. So that's how much kinetic energy my free electron would have if the frequency used was twice the threshold frequency. Yeah? Okay. So here are some example questions for you to try. So on the first one, I give you the speed of the electron and the wavelength of the light, and this time I want to know what is the work function. So again we use this formula. Here I give you the work function I give you the wavelength, and now I want the kinetic energy. You see, we're really just using this formula every time. That's all. So what we can do, see what our time is. Let me think. 50 multiplied 4 is 200 minutes, which is 3 hours 20 minutes. So we have 5 minutes left. So what I just want you to do for the last 5 minutes is just to write down the questions. You can do them at home then. Okay?
Can I take photo?
If you take the photo, then for the next 5 minutes you need to do the questions. You all okay with this?
Okay.
Yeah, alright, we'll go for it.